about the specific structure that they go through, because they're not just floating around willy-nilly outside of the nucleus, that kind of center part of the atom. There's actually a basis, a structure for what those electrons are doing. So we'll get to that in just a second. But first, there's a couple things that I wanted to hit on first. There we go. All right. So one of the big things that I wanted to mention to y'all before we get started for tonight, just so that it's not a surprise to anyone, and we'll be talking about it next week as well. But your first test, your first exam in IPC is coming up next week. So it's our midterm exam because it's the one that we take at this kind of halfway point of the semester. And it's going to cover everything that we have talked about in this class so far. So the solids, liquids, and gases, the chemical and physical properties, the protons, neutrons, and electrons, the stuff that we talk about today with the electron shells, and the stuff that we talk about next week with the mixtures and the compounds. All of that is going to be on the midterm exam. So I'll talk about it in more detail on Tuesday of next week during class on Tuesday. It's going to go live on Wednesday. So Wednesday morning of next week, the exam will open. But it is not due until Friday night. So you have all day Wednesday, all day Thursday, and all day Friday to work on the midterm. That's because it's a little bit longer than the normal kind of daily assignment homeworks that you guys get. It's also has a little bit trickier questions than some of our kind of regular homeworks. And so I wanted to give you guys plenty of time to be able to thoroughly read through it, read the questions, make sure that you understand them, and have that time to kind of work your way through it on those 3 days. So since this is being given out through the Google Classroom, what that means is that all of the assignments and notes on the Google Classroom are available to you while you're doing the exam. So if you get stuck on one point and you want to go back and maybe look at some notes that might help you out, you will be able to do that with this midterm coming up.
Mr. Stanley?
Yes, ma'am.
Will you be posting assignments as well when we have that test? Or
yeah,
so we have 2 days to do?
So since it's not due until Friday, since you have a couple days to do it, there still will be those daily assignments that get posted in order to count the attendance and to count towards your grade. I made sure to make the ones that week pretty short. So each of them is only a few questions long so that you're not spending tons of time working through those while also having to look at the exam. But yes, so you guys can't see this yet because it hasn't got an eye for you, but this is what our schedule looks like for next week. So just like with every week, there's going to be a Monday assignment, a Tuesday assignment, a Wednesday assignment, and a Thursday assignment. Only next week for week 4. In addition, there'll also be the midterm exam. That, like I mentioned, is going to be posted on Wednesday morning and is due Friday evening. Like I said, I'll talk some more about that during class on Tuesday, but I just kind of wanted to give you guys an update about it now. So you're not sort of surprised or taken aback when we come back to it next week.
Thank you, Mr. Stanley.
Yeah, no problem, Cameron. All right, so to start off today, before we actually jump into the notes on the electron shells, I wanted to jump back to the notes from last week or excuse me, not last week, but on Tuesday, just to kind of refresh us a little bit about our protons, neutrons, and electrons. So if you remember, last week we spent a lot of time on, and your homework was over, how do we figure out how many of these protons, neutrons, and electrons do we got in the atom? We mentioned that the protons and the neutrons hang out together in the nucleus. They're like this. And then the electrons kind of zoom all around them. We mentioned that the protons have a positive charge. The neutrons have a neutral charge. And the electrons have a negative charge. But the main thing that we talked about was, how do we figure out how many of each particle are in our atoms? So the first one, the number of protons, was super simple. If we look at our atom in the little box on the periodic table, the atom has an atomic number associated with it. That's kind of the smaller number up here up top. And this atomic number tells us how many protons are in our atoms. So the atomic number and the proton number are the same. The neutrons are a little bit different. They're not quite as easy. And we can figure out the neutrons by looking at and using this atomic mass number down here at the bottom. There we go.
So 36 would be our proton, and 83.80 is our neutron.
Not quite. So mass and neutrons are not the same, but we use the mass to figure out the neutrons. So you were spot on that the protons is equal to the atomic number. So in the case of krypton, that's 36. But to figure out the neutrons, we do the atomic weight minus the atomic number. So whenever you're dealing with these protons, neutrons, and electrons, the only calculation you should be doing is a minus. Not a plus, not a multiplication or division, just a minus.
You see where that got me yesterday? It was like, it gave me 20 point something and I had to round it and I put 21 type thing. I don't know.
No, that's okay. It's fine if you round it. So like for krypton, it has an atomic number of 36 and the atomic weight is 83.8, but we can say that's essentially 84. That's close enough to 84 for this class. And so to find the neutrons, we do atomic weight minus atomic number. In this case, our atomic weight is essentially 84. Our atomic number is 36. And so one atom of krypton has 48 neutrons in it. So it has 36 protons because its atomic number is 36. And it has 48 neutrons because the weight of 84 minus the number of 36 gives us 48 for our neutrons.
Okay, I see where you got that now. Okay. What
Awesome.
about the last question? Remember on that Google Doc, it was like
about the electrons.
Yes. Okay. So how do I do that? Yes.
So the electrons are also super easy. For the purposes of this class, the electrons are always going to be the same as the protons. So since our protons are positive and our electrons are negative, we want those to balance out with each other and cancel each other out. So neutral atoms, which are the atoms that we're going to be talking about only in this class, will always have the same number of protons and electrons. So for example, krypton has an atomic number of 36, which means it has 36 protons, and also means that it has 36 electrons. So the proton and the electron number are going to be the same for the atoms that we're looking at.
So it's 36.
Exactly.
And it would be like that every time. It would always be the periodic table number it gives us.
Yep, precisely.
Okay, thank you.
So, for example, hydrogen is the most simple and basic atom that there is. It has an atomic number of 1. So hydrogen has 1 proton, which means that hydrogen has 1 electron. Carbon over here is another fairly small atom. Carbon has an atomic number of 6. So carbon has 6 protons and 6 electrons.
I get you, Mr. Stanley. Okay. And what about no, I think you answered all of it, honestly. Thank you. I feel better.
Yep, no problem. All right. Anybody else have any other proton, neutron, electron number questions? All righty then. So I just wanted to review that, and especially the part about the electrons, because the notes for tonight are specifically looking all about these electrons. Oops, that's the assignment. We don't want that. We want the notes. All right, so today we're not just going to be talking about electrons. We are going to be talking about things called electron shells. So for our electrons that we were just talking about, for our neutral atoms, our neutrally charged atoms that we're working with in this class, the electrons and the protons have to equal each other, right? Hydrogen has 1 proton, so it needs to have 1 electron. Carbon has 6 protons, so it needs 6 electrons. Krypton has 36 protons, so it needs 36 electrons. So last week, we talked about how our protons down here hang out in the nucleus, in sort of the center area of the atom, right? So you've got your protons and your neutrons, and they're together, kind of hanging out, grouped up in the nucleus. Electrons are outside of the nucleus, so they're kind of in these clouds around the nucleus, kind of whizzing around the outside. But electrons aren't just randomly flying around. All right, it's not just kind of like they're zooming all around each other with no sort of pattern. There actually is a structure to the way that electrons are filled in around our atoms. And the way they do this are by orbiting in what are called shells. So there are kind of these invisible boundaries around the nucleus of the atom, that center area. And we call those boundary lines shells. And each cell around an atom can only fit a certain number of electrons. So in this class, we're only going to look at the first 3 electron shells: shell 1, shell 2, and shell 3. So our first electron shell can only fit 2 electrons on it before it gets full. So that's it. Once it hits 2, it is full of electrons. So like hydrogen, for example, that super duper basic atom, he's only got one little electron on his shell. Helium is the next one up from hydrogen. He has an atomic number of 2, which means helium has 2 protons and 2 electrons. So this first shell of helium is full. We've got 2 electrons on there. And so it is a full shell around helium. If you have more than 2 electrons in your atom, like most atoms do, that means that you have to start filling out your second and potentially even your third shell. So our second shell and our third shell can both fit up to 8 electrons. Not 18, so I'm going to go ahead and tell you right now, if you try to Google the number of electrons on the third electron shell, it'll tell you 18 because it's counting all of the electrons that are filling up underneath. But in reality, on only the third shell itself, only 8 electrons can fit on there. So what does this mean for a couple different atoms? Well, let's start with lithium. So lithium is right after hydrogen and helium. So lithium right here is the third atom in the periodic table. So lithium has 3 electrons. So we put the first 2 electrons on shells 1 and 2, but we still have that 1 electron left over, right? That guy goes on the second shell. So we fill up these electron shells from smallest to biggest. So we start adding electrons to the first shell, and then if that gets full, we move out and start filling up the second shell. So in the case of lithium, we put down the first 2 electrons on the first shell, but then that one's full, and so we have to put the third electron on the second shell. In the case of carbon, carbon is atom number 6. So carbon has 6 protons and 6 electrons. So carbon can fit 2 of those 6 electrons on the first shell, but then it gets all full. And so the remaining 4 electrons have to go on the second shell. So there's 6 electrons total in carbon. 2 of them fit on the first shell, and then the remaining 1, 2, 3, 4 go on the second shell right here. But like I said, the second shell can potentially fit up to 8 electrons on it, which is the case with neon. So neon is atom number 10 on the periodic table. So neon's got 10 electrons. So we can put the first 2 electrons, number 1 and 2, on the first shell, and then electrons 3, 4, 5, 6, 7, 8, 9, and 10 go on the second shell. So 2 on the first shell and 8 on the second shell give us 10 total electrons. So again, we start with the first shell and then start building out from there. Our first shell can only fit 2 electrons on it, and then shells number 2 and even potentially 3 can fit 8 electrons. So neon, we said, has 10 electrons, so we completely fill up the first and second shell. But what about if we go up one more atom on the table to sodium? So sodium is one of those weird atoms where even though the symbol of sodium is Na, we call it sodium. Sodium has 11 electrons on it. It's atom number 11, so it has 11 protons and 11 electrons. So we start filling in the electrons the exact same way. There are 2 on the first shell, and then we can fit 8 more total on the second shell. And then after we put the 2 on the first and the 8 on the second, that's only 10 out of our 11 electrons. So that very last guy, that very last little electron, has to go out on the third shell out here. So 2 on the first, a total of 8 on the second before it gets full, and 1 more on the third gives us 11 total electrons. So the exact same thing occurs for silicon right here. Silicon has an atomic number of 14. So it has 14, I can't even put up 14 fingers, but it's got 14 protons and 14 electrons. So just like with sodium, we start filling in from the first. So 1, 2 electrons go on that first shell. Then the first shell gets full. We can put 8 more electrons on the second shell. But then the second shell gets full, and we've only put 2, and 8 on the first 2 is 10. But silicon still has 4 more electrons to go. So we put those last 4 on the third shell. So that first shell got 2, and then it was full. The second shell got 8, and then it was full. And then our third shell got the remaining 4. If we wanted to look for an atom that completely filled up the third shell, we could look at something like argon. So argon is kind of similar to neon, except while neon has 10 electrons, argon has 18. So its atomic number is 18. It has 18 protons, and so it's got to have 18 electrons. So in argon, again, just like all the other ones, we start with the first ring and then start filling out. So we put 1, 2 electrons on the first ring. Obviously, we've still got a lot left over. We put 1, 2, 3, 4, 5, 6, 7, 8 electrons on the second ring. Now the second ring is full, but we've only put down 10 of our 18 total electrons. So then on our third ring, we put down the remaining 8 electrons, right? So 2 on the first ring, plus 8 on the second ring, plus 8 on the third ring, gives us a total of 18 electrons for argon. And so in an argon atom, it has a completely full first shell, second shell, and third shell. So that is how we determine where the electrons go on a particular atom. We figure out how many electrons that it has. We then start adding those electrons to the first ring. If that first ring gets filled up, we start adding them to the second ring. If the second ring gets filled up, we start adding them to the third ring.
Are we ever going to have more than 3 rings?
Not for this class. So obviously there are many more atoms that are bigger than argon, with even more electron rings around the outside. I think all of the remaining, like the 4th and 5th and 6th shell, also have 8 electrons. But we're not going to worry about those for this class. So in this class, all you have to know about is first shell, second shell, third shell.
Okay, thank you.
Yep, no problem.
I'm sorry, I had to step out real quick, but I'm back.
Oh, no worries, Cameron.
Thank you.
So I'm going to work some examples of these with you guys here in just a second. But does anybody have any more questions about kind of the basics of the electrons and the electron shells? All righty. So I'm going to go ahead and open up a Jamboard so I can kind of do a couple of these and like show you how I would go about actually doing this if I had like a blank sheet of paper. So there's a link to it in the chat if you want to go in and look at it in person. But I'm also going to share the video of it on our class right now so that if you just want to watch along and kind of talk along with the video, that is fine as well. All right. So all right, I'm going to do a couple of examples and kind of have you guys help me figure out how to set up these electrons. So the first one that we're going to do is nitrogen. So let me grab and right here. Ooh. Let's try doing it a little bit more fun. Whatever. All right, so nitrogen is, actually, hold on, I'm gonna redo this. So nitrogen is atom number 7. And then let me add in our rings. So if nitrogen is atom number 7, then how many electrons does nitrogen have?
7.
Bingo, exactly. So nitrogen, I'm going to write it up here in the top just to help remind us. Nitrogen has 7 electrons. And a lot of times when you see people write out electrons, they'll make a little E- sign as kind of a reminder that electrons are negatively charged. So nitrogen has 7 electrons. So let's figure out how many electrons are going to go around each shell of nitrogen. So we start filling in our first shell first. So always remember, first shell first. So how many electrons can we fit on the first shell for nitrogen?
2.
2, bingo. So I'll add in 2 little raggedy dots here. Or actually, let me see if I can do like this kind of thing. That did not work as well as I thought. We'll just go with the little highlighter brush and a little bit marker. All right. So 1, 2 electrons. But now the first shell is full, right? Can't put any more on the first shell. That's not allowed. It's got its 2. But we still have some electrons to go, right? We're not done putting down electrons for nitrogen. So how many more electrons do we have to put down for nitrogen?
5.
5, exactly. So we put the 2 down already, but now we have 5 more. So can we fit all 5 electrons on the second ring?
Yes.
Yes, bingo. That is correct. 1, 2, 3, 4, 5. So 2 on the first ring and 5 on the second ring, because like we've been saying, we can fit up to 8 electrons on the second ring. So 5 fit on there just fine. So do we need to put any electrons on the third ring for nitrogen?
No.
No, precisely, correct. So nitrogen does not have a third electron ring. I purposely put it up there to see if I could trick you guys, but you guys are too smart for me. So nitrogen only has the first 2 electron rings because that's all that it needs. It only needs those first 2 shells. So in the case of nitrogen, we have 2 electrons on the first ring and 5 electrons on the second ring, which gives us a total of 7 electrons, which is what we said nitrogen has for it. Precisely. All right, so you guys handled that one pretty well. But let's try a little bit different one. We'll do blue this time. It's kind of more aluminum-y type thing. So aluminum is an atom, and aluminum has atomic number 13. Let's see, 1, 2, 3. So if aluminum has an atomic number of 13, then how many electrons does aluminum have?
13?
13, precisely. So aluminum's got 13 electrons. I'm going to write that down up here so that we remember. Try to see if it works. So aluminum has 13 electrons. So let's see how many we can fit on each ring. So starting off with the first ring of aluminum, how many electrons can we fit on this first ring here? First shell.
2.
2, precisely. That's not at all what I wanted to do. All right, that's good to know. Marker? I don't really know how marker and pen are different, but it says that they are. All right, so 1, 2 on aluminum's first ring. But obviously, we still have quite a few electrons to go to get up to 13. So there's our first 2. So let's see how many we can fit on this second ring. So I have 1, 2 on the first one. And then we can fit number 3, number 4, number 5, number 6, number 7, number 8, number 9, and number 10 on the second ring. So now we've put down 10 in total. There are 2 on the first ring, and 1, 2, 3, 4, 5, 6, 7, 8 on the second ring. So can we fit any more electrons on ring number 2?
No.
No, we cannot, precisely. So we have to go out to our third shell out here. So we've already put down 2 on the first shell and 8 on the second shell. So how many more electrons do we have left in aluminum?
3.
3, precisely. 1, 2, 3. So 2 on the first shell plus 8 on the second shell plus 3 on the third shell gives us our 13 electrons in aluminum. So in this one, we did have to go out to that third shell because we filled up our first shell and we filled up our second shell, but we still had some electrons left over. So we had to go out to shell number 3. So that is sort of the basic game plan for if you ever want to go in and figure out the electron shells. You figure out how many electrons you're working with, fill in the first shell. If that gets full with 2 before you run out of electrons, start filling in the second shell. If that gets full with 8 before you run out of electrons, you move out and start filling in the third shell out here. All right. Any questions about the electrons or the electron shells?
No, sir.
All right, cool. So here is a little bit nicer view of what a couple of those electrons might look like. Let's see. There we go. So here's our nitrogen atom. Remember, we had the 2 on the first shell and the 5 on the second shell to give 7. Neon was that one atom we talked about a little bit ago where it has a full first and second shell. So 2 and 8 together give us 10. And then aluminum we just did has the 2 on the first shell, the 8 on the second shell, and the remaining 3 on the third shell gives us our 13 aluminum electrons. All right. So one interesting thing that scientists noticed when they first started observing and measuring atoms is that atoms really want their shells to be full. So atoms are kind of the most, I like to call it happy, but I mean they're atoms, so they can't really have feelings or emotions. But they're the most stable, they're the most kind of conserved when their outer shells are full. And so sometimes what this means is that they'll work together with other atoms to kind of share or donate some of their outer electrons so that they can have nice full electron shells. So we're actually going to talk about this a lot more next week when we talk about chemical bonding. But this is the basic idea around this. So like hydrogen, for example, out in nature, in the world around us, you essentially never encounter just one single hydrogen atom on its own. It's pretty much always 2 hydrogen atoms combined. And so we call that H2 or H2 gas. So the reason why that happens is that one hydrogen that has 1 electron on its first shell and another hydrogen that has 1 electron on its first shell will basically share their electrons with each other so that they both feel like they have 2 electrons on their outer shell. And that makes them happy because they want 2 electrons on that first shell. So some atoms do it this way, where they'll share electrons in order to make a full shell. Other atoms will kind of donate their electrons so that they can lose an outer electron and have a full second shell, or they can gain an outer electron in order to fill in their almost full shell. So with the example of sodium and chlorine, sodium has 1 electron on its third shell. Chlorine has 7 electrons on its third shell. So they're both very close to having a full set of electron shells, right? If sodium could just somehow get rid of this 1 electron, then it would have a full first and second shell and be happy. And if chlorine could somehow gain 1 more electron to fill its outer shell, then it would have a full outer third shell and it would be happy. So what will happen is that these atoms, sodium, will essentially donate 1 of its electrons to chlorine in order so that both of them can have these full electron shells. So this actually creates something that you probably use in your almost everyday life, which is table salt. So the molecule sodium chloride, which is formed when sodium and chlorine loan the electron from one to the other, it causes them to kind of stick together for reasons that we'll talk about next week. But it forms the compound sodium chloride, which is salt, table salt. So, but the basic idea is electrons wanting these outer shells to be full, to completely fill in all of their electron shells. So what this means is that it causes atoms to be different in one of their chemical properties called reactivity. So we talked about the other week about some chemical properties of matter have to do with if a atom is more or less likely to undergo some sort of reaction with other ones. So like whether or not something can light on fire easily is an example of a chemical property. How reactive an atom is another example of a chemical property. So reactivity is how easily or how quickly one element combines or reacts with other elements or compounds. So like pure sodium, for example, is a very, very, very reactive metal. All right, if you expose it to just the air or a little bit of water, it will explosively react with the molecules in the air and create this big kind of light and smoke and heat reaction because it is very reactive. The reason that it is very reactive is...
I'm sorry, I have a question.
Yeah, go for it.
Are we supposed to be seeing like the PowerPoint, the screen? Are you supposed to be sharing? Oh, because we can only see you, like we don't see the presentation.
Oh, that's weird. Is anybody else having that issue?
I see both the presentation and then I see you.
Hold on, let me try re-sharing the presentation. Let's see. So click that button, and then now you should only see me. And then let me click this button again. Boop, boop. And all right, now is everybody able to see the presentation with the big lit up beaker?
Yes.
All right. Awesome. Thank you for giving me a heads up about that. Sometimes you just got to turn it off and turn it back on again to help make it go. All right. So some atoms, some elements, one of their chemical properties is that they are very reactive. Specifically, elements that are very empty or almost full with their outer shells are the more reactive elements. So sodium, for example, has an almost empty outer shell. It just has one electron on its third shell, which makes sodium very reactive. Chlorine is also very reactive because chlorine has an almost full shell. So they're both extremely reactive elements, but for the opposite reason. So elements that have a very empty or an almost full outer shell are the more reactive elements. So like over here, sodium is number 11 right here. So all of these elements that are in this column with sodium. So on the periodic table, we call columns groups. So lithium, sodium, potassium, rubidium, cesium, and francium. This first group, all of these guys have only one electron on their outer shell. So they have a very empty outer shell. So all of these elements are extremely reactive. They have very, very, very high reactivity. These guys in group 18 over here are the exact opposite. Our group 18 atoms are extremely non-reactive because they have completely full outer shells, right? So helium has 2 on its outer first shell. Neon has 10 electrons, so it has 8 on its outer second shell. Argon has 18 electrons, so it has 8 on its outer third shell, and so on and so forth for the other atoms in this group, in this column. So all of these guys have a completely full outer shell. So they're like fat and happy, basically. Their outer shell is full. They don't want anything to do with any of these other atoms over here in the periodic table. They're like, I'm good. I don't need to do any reacting. I've got all my electrons that I need. I am nice and happy. So if the shell is completely full, then it's essentially they have extremely low reactivity. They're almost non-reactive with other elements. But if they have an extremely empty shell, like these guys, or an almost full outer shell, so chlorine that we were talking about earlier, number 17 right here, chlorine only has one, or it's only missing one electron from its outer shell. Same thing with francium and bromine and iodine. All of these guys are only missing one electron from their outer shell. So that makes them reactive as well, because they really want to react with something and get that final electron in there. So very empty and almost full are very reactive. Completely full is very non-reactive. They are the fat and happy group over here. So again, we'll talk a little bit more about reactivity and about how those atoms share and borrow electrons. A little bit more at the end of next week, I believe, is when we'll get to that. But the final thing that I want to talk to you guys about tonight is some of the different groups of atoms that we have on our periodic table. So you may have noticed that we have some different colors spread out on our little mini periodic table here. And that's not just to make it look nice and pretty, but that's because we can group our atoms into 3 basic categories. We have the metals, which are in yellow and are the vast majority of atoms on the periodic table. We have the nonmetals in green. That's this kind of small group over here on the very far right of the periodic table. And then our metalloids are this kind of funky in-between purple group right here. So they kind of make this little zigzag in between the metals and the nonmetals. So in the metals, we've got things like copper and nickel and cobalt. We've got iron, aluminum, lead, gold, silver, plus some things that you might not expect, like sodium and potassium and magnesium. These are all metals. And then on our nonmetals, we've got some guys you may have heard of. We've got our oxygen, we've got our helium, we've got our carbon, neon, krypton that we were working with earlier this week. Those guys are all nonmetals. So metals, nonmetals, and metalloids all have slightly different properties from each other, with the metals and the nonmetals being very different, and then the metalloids kind of falling somewhere in between. So first up, the one that you guys probably have the most experience with in your day-to-day life, whether you know it or not, are our metals. So metals tend to be shiny, right? So whenever you think about the characteristics of metals, I want you to picture in your head aluminum foil that you probably have at your house, right? So metals tend to be shiny. They are usually solids at room temperature, right? So the aluminum foil, my gold wedding ring, the silver that's in your necklace, it's all solid unless you get it really, really hot. There are a couple cool exceptions to this. Like if you've ever heard of the metal mercury, mercury is one of the few metals that is liquid at room temperature. And so it's this cool silvery liquid. But if you ever see liquid mercury, do not touch it. It is very toxic and poisonous. So don't touch it with your bare skin. But for the most part, most metals are solid. Metals have a couple different characteristics in terms of how we can shape them. So not only are they very malleable, which means that you can hammer them flat down, right? So if you think about a coin that's made out of metal, your coins are very flat. That aluminum foil in your cupboard at home is a flat, thin sheet of metal. If you took my wedding ring and put it into a big press and squished it down, it would probably squish down into like a flat little disc. And so that's what we mean by malleable. It means that we can squish and hammer down metals without them breaking or shattering. Metals are also ductile, which means that we can stretch and twist them out and pull them into a wire. So like if you've ever done any sort of electrical work on your house, or like, for example, a couple weekends ago, my dad was over at my house helping me put in some new ceiling fans that we bought. And we had to do some twisting and connecting of different metal wires. And so the reason why wires are made out of metal, well, one reason is that it's easy to kind of twist and shape metal. The other reason why wires are made out of metal is that metals are very, very highly conductive, which means that heat or electricity can very easily pass from one side of a metal to another. So this is the reason why all of your cookware is probably made out of iron or aluminum or some combination of the two, maybe copper. Because when you put it on the stove, you want the heat coming off of the stove to go really quickly into your food that you're cooking. And so the conductivity of metals allows you to do that. Same reason why whenever you're stirring food or you're stirring like a boiling pot of water, you're probably using a wooden spoon instead of a metal one, right? Because if you leave that metal spoon in a boiling pot of water for a couple seconds, the end of the metal is going to get really hot, right? Probably too hot to hold. Whereas a wooden spoon, you can leave it in there for a little bit, pick it up and stir it every once in a while, and it'll be totally fine. Because wood is not conductive, but metal is. This also works for electricity. So the reason why all the wiring going through your house, a lot of it is made out of copper, is because copper is an especially good conductor of electricity. Also, if the reason why you want to keep any metal away from your electrical outlets or something, right? Please do not ever do this. But if you were to like jab a plastic fork into your electrical outlet, nothing is really going to happen, right? The electricity has a really hard time going through the plastic and getting to your body. If you take a metal fork and shove it into your electrical outlet, you're going to have a really bad time because that electricity will shoot through the metal and right into your body, which is not a good thing. So metals are shiny and solid. You can squish them down flat or twist them out and pull them into a wire, and they are very conductive. They transfer heat and they transfer electricity really easily and efficiently. Nonmetals, on the other hand, are basically the exact opposite of metals. So nonmetals tend to not be shiny. So think of like, when you're thinking of nonmetals, you can kind of think of like some of the minerals that are in like rocks and deposits and stuff that are underground. A lot of times will be made out of a lot of nonmetals. And so like this brick of sulfur right here, it's not nice and shiny, right? It's not shining the light like a metal is. Nonmetals are mostly gases at room temperature. So like oxygen, chlorine, hydrogen, helium, nitrogen, they're all gases at room temperature, right? They're all floating around you as gas. You have to make them really, 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 really cold to get them down into liquid form. Nonmetals are very, very poor conductors. So plastic, for example, like I was just talking about, is mostly made out of carbon. Carbon is a nonmetal, and carbon is a bad conductor. That's the reason why it's hard to get, or you're not going to get shocked if you stick a plastic fork into the electrical outlet. Not that you should do that. That's still a bad idea. But it's less dangerous than a metal one. Also, in nonmetals, when they are solid, they are very, very brittle, meaning it's very easy for them to shatter and break apart into a billion million pieces. Whereas our metals, we could squish down flat or twist them out and turn them into a wire. Nonmetals ain't going to do that. They're just going to shatter and break apart on you if you try to pull something like that. So like I said, basically the opposite of metals. They tend to be gases. They're very bad conductors. If you do make them solid, they just kind of shatter and break apart if you try to do anything with them. And they don't end up creating this kind of, having this kind of shiny exterior. So nonmetals and metals sort of on opposite sides of the scales. Metalloids, if you remember on the periodic table, they're kind of an in-between group. And in terms of their properties, they're also sort of an in-between group as well. So there's not a lot of metalloids. There's only 7 or 8. They tend to be solids at room temperature, like metals are. However, they tend to be very brittle and hard and breakable, like nonmetals are. So even though they're mostly solids, they are also very brittle and very prone to crumbling or breaking. Metalloids are what are called semiconductors, which means that under certain conditions, they are very, very good at conducting electricity, but under other conditions, they do not do it very well at all. And so it has to be under a certain temperature and pressure conditions where their conducting ability really kicks off. But otherwise, if everything isn't exactly right, then they do not do it very well. So metalloids are actually very important for computer chips. So a big metalloid is silicon. It's what makes up a lot of sand and a lot of glass. And it also is what makes up a lot of the parts of the computer chips that go into your phone, your laptop, your desktop, your tablet. It all has chips based off of silicon semiconductors in there. So the computer scientists were able to figure out a way to embed silicon in these chips in the right conditions where it would be an extremely good conductor. So metalloids, in between group, they are solids like metals, but they're very brittle and breakable like nonmetals. And then they can conduct heat and electricity, but only sometimes under certain special circumstances. So we have our metals, our shiny, malleable conducting metals in the middle here. In general, the more reactive metals tend to be over on the left-hand side, like these guys that I talked about earlier. And then as you move to the right, the metals tend to become less and less reactive. Our nonmetals over here, again, very brittle, bad conductors, tend to be gases. They actually have the opposite situation where the left-hand side nonmetals tend to be less reactive, and then they get more reactive as you go to the right. So like group 17 right here with the francium and the chlorine, or no, the fluorine and the chlorine and the bromine. These are all very, very, very reactive nonmetals. But then, like I said, the very last group, the last column over here, is extremely non-reactive. So we'd go from very reactive to very, very non-reactive, because these guys have that completely full outer shell. So they're sitting fat and happy over here on the far side of the periodic table. And then again, we have our metalloids here in the middle, where they're solid, but they're breakable, and they only sometimes conduct electricity. So carbon is an extremely important nonmetal for living organisms. Like you and me, for example, are mostly carbon-based life forms. So carbon is what we use to construct most of our cells. Carbon is what we burn for energy inside of our bodies. All of that stuff is based on carbon. Oh, and then the final thing that I wanted to mention is that that very, very last group of nonmetals, the super non-reactive ones, the scientists gave them kind of the funny name of noble gases. They call them this because they are gases. So these are all gas atoms over here at room temperature. And they are the noble gases because they are they're so non-reactive that it's like they don't want to mingle with all of the other lower class atoms over here. These are the noble gases. They can't be bothered associating with all of these other atoms over here. So because they're so non-reactive and they only like to stick with themselves, scientists gave them the kind of funny name of the noble gases. Alrighty, so I believe that is the end of the notes for tonight. Does anybody have final questions on reactivity, metals, metalloids, nonmetals, anything that we were just covering just now?
No, Mr. Stanley, thank you. I have to
Oh.
go. I'm gonna go to HB real quick, but you have a good night, okay? And I'll get
All right.
the homework done.
All right, sounds good. Thanks, Cameron. Anybody else? Any other
Of course,
final
bye.
questions, either about the metals and nonmetals, or even going back to the electron shells from earlier? Any final questions about any of the notes that we covered here tonight?
No, thank you.
All right, so then the last thing that I wanted to do with you guys was quickly show you the for both tonight and for Monday evening. So our Thursday assignment has to do with those electron shells, where I give you the atom oxygen has a atomic number of 8 and an atomic mass of approximately 16. And so for the first part, it's kind of a review from some of our earlier stuff, where I want you to tell me the protons, neutrons, and electrons for oxygen. So that's kind of the first part. The second part, I want you to go through the electron shells. So I want you to tell me, based on this information that you have up here about oxygen, how many electrons are going to go on the first shell of oxygen? How many electrons, if any, are going to go on the second shell? And how many electrons, if any, are going to go on the third electron shell around oxygen? So 6 questions, 3 of which are kind of a review of some of the stuff that you're already working on and doing so well with. And then, so that'll finish up your assignments for this week, week 3. And then your first assignment for next week will be about those metals, metalloids, and nonmetals that I mentioned at the end of class today. So this will go up on Monday to kind of help jog your memories about the notes from tonight. And so I have a whole bunch of descriptions, characteristics listed out over on the left here. And so for each one, I want you to tell me, does this describe a metal, a metalloid, a nonmetal, or a combination of those two? So there could be more than one substance that matches the description. So for example, if something matches, like if you think that all of these are shiny, then you would say, yep, all of these are shiny. If you just thought that metals were gases at room temperature, you would say that. If you thought that both metals and metalloids were brittle and solid, then you would pick both of those. So you're basically matching the description over here on the left with each type of substance that it describes. It could just be one, it could be all 3. That's for you to figure out. So that it is the assignment that'll be coming up to kind of help us get back in the swing of things on Monday. All right. So does anybody have any final questions about the notes from tonight or the assignments coming up for today and for Monday?